And so the rabbit hole goes deeper. Let's empty the recycle bin. So we'll do this. And before we jump into it here, what we're going to do is you can sort of nest your flags under the scripts that they are under their parent script, if you will, is what we're going to say. So the way that you do that is you just sort of highlight it and then you just click and drag it, and you can see the little line there changes. This, if we let go right here, it will just put it right there in the middle in the address list, and then you could drag it down to the bottom, and then you see the solid line that goes all the way across. Now it moves down to the bottom. If you actually link it right up to a script, and then the line stops right there, visually that's Cheat Engine's way of telling you, I'm going to nest this under whatever the script is. So let's do that. And then you also see that there's a visual thing here where it sort of provides some indentation for you. That's not very nice. So what we're going to do is we're going to right click on the script and go to group config and just say hide children when activated. What that's going to do is basically when the script is active, it will show the flag, and then if the script is not activated, it will hide it just like that. So you don't even know the flag is there until the script is enabled, which it can't be enabled right now because it's not linked to a process. And then another one that is generally useful is deactivating this entry deactivates children. We don't have to worry about that so much when it comes to flags, but and the reason why is because when you disable your script, the flag is going to be destroyed anyway, so it's not really going to matter. So let's maybe show this off a little bit. We need to spend a point and then get rid of a point. So there's that. Now we can link to the process. Or we could have linked to the process before, but we still would have had to go through all that garbage. There you go. The script activates. Now you can see flag infinite karma right here. You can active, deactive, whatever. Makes no difference. The initial value is 1. We'll demonstrate good practice. Disable the script. Now go into the script and modify it. We want the initial value to be 0. And with those small changes, we will save it. Yep. All right. So we're going to close this. We're going to close this. I'm going to bring this back up. I've sort of disabled user access control, so maybe the mouse won't be flying off into the upper left corner here. It only took me, 15 hours to think of that, or I don't know how long, but so we spent some time talking about the flag and how we're going to set it up and what DB does. And basically, flag infinite karma is going to be 1 byte or 8 bits, so you can fit a max of 8 bits of data in there. But we only need 2, 0, and then other values. We're not making any distinction about that. So how do we sort of branch our script off? Let's codify what it is that we want to do first, and then we will talk about how we will do it, and then we will go ahead and start doing it. What we want to do is we want to make it so that when we enable our script, I'm going to get rid of hide children when deactivated for now so that I can point to things. When we enable the script or script karma and the AOB scans return memory addresses and they succeed, and then it's activated, we want to be able to set some value to flag infinite karma so that by default, flag infinite karma will have 0, and our script, even though it is activated, will check the value of flag infinite karma, and if the value of flag infinite karma is 0, it will do nothing. Only if the value of flag infinite karma is non-zero will our script actually do something. And if you have familiarity with higher level languages or Visual Basic, Python, any language, frankly, with the above assembly, what you will be familiar with is just basic control flow. You have if statements, you have while statements, for statements, and all kinds of branching and just some basic things. You can even go to Wikipedia and type in, let's say, control flow. Do we get something there? In computer science, control flow refers to the order in which the individual statements, instructions, or function calls of an imperative or a declarative program are executed or evaluated. It's a lot of wordiness there. A control flow statement is a statement whose execution results in a choice being made as to which of two or more paths should be followed. The kinds of control flow statements supported by different languages vary but can be categorized by their effect. Continuation of a different statement, an unconditional branch or jump, which is exactly what we're doing in our script. We don't care about what the value of anything is. Whenever the processor hits our unconditional jump right here, or just JMP, it's not even going to worry about should I do this or should I not do this. We are telling the processor, do it. I don't care what the value of anything is. I know what I'm doing, so just do it, and that's it. Executing a set of statements only if some condition is met, i.e. a conditional branch. That's exactly what we're talking about with our flag. We want to conditionally branch our control flow of our script based on the value of flag infinite karma. Executing a set of statements 0 or more times, that's looping. A set of distant statements after which the flow of control usually returns, that's sort of a general way of categorizing functions. Stopping the program, preventing any further execution, otherwise known as halting. We're not going to deal with any of that. Well, we'll just stay on that page for now. So let's see. I doubt Wikipedia has a CMP. Let's just do that. It's going to be disambiguation. Science, computing, comparison, and computer programming. There's that. All right. Well, it's obviously going to be something like that, but let's see what they have to say about comparison. Yeah. I doubt it's going to talk about it in the context of assembly languages. I wouldn't expect it to. It's probably a good thing that it does not. So let's hit F1. We're going to go to the help file. Cheat engine help file, tell me about compare. Or more specifically, tell me about the CMP assembly instruction. Does it do that? You have that, and then you have that, and then deck, and then sub, and then you have jump, and you have call. Did we skip it? Let's just search it for CMP. How about that? It's probably a better way to do it. There are also conditional jumps. So let's back up a bit. Then there are jumps, loops, and calls. Jump, JMP. The jump instruction is the easiest as it changes the instruction pointer to the location the JMP instruction points at and continues from there. We've purposely been glazing over the EIP register and the instruction pointer and whatnot, or the program counter, whatever you want to say, and we're going to continue to do that for now. There are also conditional jumps that will only change the instruction pointer if a special condition has met, or has been met is probably the better way to say that. For example, set using the compare instruction. Another typo. So what is basically being said here is that you can test for some series of, or test for some condition relative to one value, or I'm sorry, you can test for some condition for one value relative to another value, and then you can execute a different set of instructions based on the result of your comparison, your testing, whatever you want to say, your conditional. So let's keep going. Bit flags, status flags. We have to get into that at some point, but I just want to go over that. What's the difference in byte type? Let's go to basics 1. Opcodes, registers, general purpose, segment, pointer, stack. Yep. So there's the move. Does it go over the add? There's add, sub, multiply, divide. Then you have the bitwise operators. Then you have add, and then NOP, and then bit shifting, and then that's it. And you have floats. That's the floating point. So you have conditional jumps here. So let's read a little bit here. Let's talk about flags. What the hell are flags? That's a good question. Well, it's not that difficult to understand. Well, I don't know. I'm going to reserve my own judgment on that. The flag register. So basically the flag register. There is similar to how you can see in the memory viewer, and we've talked about sort of how registers are hardware variables and things like that. If you just open up the memory viewer here and you look around, there's EDI, EBP, ESP. These are, as we've said, these are all registers. There are registers that you generally will not see in the memory viewer because they are used behind the scenes to implement certain functionality that is required for modern computing to happen on the hardware level. The compare instruction is the first and foremost, and I think the most explicit example of that. So when you do a compare, in the move, we are saying take one value and store it in another or another location. As a sort of there's no corollary between the CMP and the move. What the compare is doing is it's saying here's one value EAX, and then here's a second value, some memory location. Um, I want you to compare these two values. Now, the question that you should be asking yourself is, well, where is the result of this value stored, or of this comparison stored? It's not stored in EAX, because then the comparison would be meaningless, and it's not stored in this memory location, because then the comparison would also be meaningless. So there has to be some third location that the result of the compare operation is stored in, and that location is the flag register, or registers as the case may be. So let's keep reading. The flag register has a set of flags which are set, unset, depending on calculations or other events. Here are the more important ones. The zero flag. This flag is set when the result of a calculation is zero. Compare is actually a subtraction without saving the results, but setting the flags only. Then you have the sign flag. If set, the resulting number of a calculation is negative. Then you have the carry flag. The carry flag contains the leftmost bit after calculations. That has to do with just sort of arithmetic and things like that. And we're never going to drill down to the level of ZF and SF. You don't have to test these things individually, thank God. You just the unconditional jumps, or the conditional jumps do that for you. So you will notice that almost every time after a CMP, this is not a hard and fast rule, but this is sort of a good rule of thumb. After a compare, you will almost always see some sort of conditional jump. It'll be JG, JNE, JLE, or something like that. And the reason why you will see that is because this assembly instruction, the conditional jumps, automatically test the flag registers for the result of the comparison. So there's sort of an implicit assumption built into the assembly language that if you're doing a conditional jump, that at some point prior to this conditional jump, you did a compare or a test or some sort of you executed some set of instructions that will set the value of the flag register to whatever it should be for the conditional jump to operate in a sane way. And the way that that happens is, again, implemented under the hood. When you do a compare, the compare will test one value relative to another value, and it will automatically store whatever the result of that comparison is in the flag register. And then after that, when you come down and you do the conditional jump will automatically check the flag register to see what is the result of the previous comparison. So that's a whole lot of under the hood stuff. And this is why I have sort of pushed this back, and so we were able to build up a basic scaffold of our script without having to go into any of this detail, and it should be apparent why, because we don't need to ever, up to this point, who cares about the carry flag or the sign flag? Introducing all this stuff before you understand what an unconditional jump is just meaningless fluff, because you have no context in which to assimilate this information. There is other flags, some of which you will never use, so I won't talk about them. A man after my own heart. So let's talk about jumps. Here's a list of opcodes for jumps. Opcode meaning condition. Here's JA, jump if above, JAE, jump if above or equal. I'm not going to read them all, but you can see JNG, jump if not greater, signed. Jump if not greater or equal, signed. What is a signed sort of qualification? It's just letting you know that it's doing a signed comparison. As you can see, jumps have conditions set to them from a previous calculation, test, or compare. We just said that, and this guy is reiterating it, so we know we're not crazy. Let's look at this example. Test EAX EBX, jump if equal to some address, and then do the move EAX EBX, and then unconditionally jump to some other address. Do note that these addresses right here are exactly the same. So what this really, before we go down and read more about this, what is really going on here is that there is some comparison or testing being done relative for EAX relative to EBX, and if these are equal, if EAX is equal to EBX, it will jump to this memory location. If it is not equal, then it will move EBX into EAX so that now they are equal, and then it will jump to this memory location, which is the same as this. So in this set of 4 assembly instructions, you can see that right away you've been able to codify some sort of logic that says, hey, if they're not equal, I want to make them equal, and then I want to resume execution at exactly the same spot that it would have resumed execution if they were equal to begin with. So this gives you incredible power. And let's just keep reading. This little example basically tests 2 values to see if they are equal. If so, the program will move the value 1 into the 0 flag, thus allowing the conditional jump to go to a memory location to execute there. So, how does jump equal know that EBX is equal to, or EAX is equal to EBX? These 2 values are the same. It's under the hood. You don't have to worry about why. You don't have to test the ZF flag or the 0 flag yourself. It's just built right into the conditional jump or the JE instruction. If it wasn't equal, the program will move 0 into ZF. Again, that's all under the hood here in this one test instruction. So if they are not equal, then the 0 flag will actually have a 0 bit in it, and the conditional jump will see that, and it will say, oh, okay, so they're not equal. I'm not going to jump to this location. I'm just going to go to the next instruction, which is this, and then I'm going to do an unconditional jump to this memory location. So if they were not equal, the program will move 0 into ZF and will skip the JE instruction, then move the value into the value in the EBX register to the EAX register, forcing them to be equal, then doing an unconditional jump to the same memory location as indicated by here and here. Games can use this. Some games can have a real address for values and what I like to call ghost address. The ghost address is where the value to be shown on the game is used, but if a check like above exists, no matter what you force into that address will revert back to the real one. Not going to worry so much about that. We will at some point, but let's see. Anyone trying to scan for a game may have come up against this. Okay. Other opcodes that can be used is CMP, register/value. Compare 2 values and move 0 or 1 into appropriate flags. That's what we will use the CMP. That's enough for now. I've taught you the basic ASM opcodes, floats, and conditional jumps. This should be all you need to train a game. Let's go over here. Code injection in the auto assembler. See if we can maybe find a little something about search for CMP. It probably won't have as much context. It's just going to say do this and do that and then figure it out. So how are we going to use this to our advantage? What we're going to do is we're going to do a compare down here in our entry function, and then we're going to use a conditional jump to evaluate the result of that compare, and that's it. If we will do a compare, we will come up with some way to say what we will really do is write in assembly. We will say compare flag infinite karma 0, and then we will say jump if equal to some location, some label, some function. And then if it is not equal, which means that it is a non-zero value, which we will interpret in our script to be true, then we will go to some other location, some other function in memory, and we will say, hey, yeah, they want infinite karma. And then we will basically, what we will do is we will push 64 into EAX and so on and so forth. And that is sort of the basic skeleton that you're going to use when you want to codify, when you want to have a flag outside your script that the user can push a value into, and then you want to test that flag and do conditional execution in your script. This is how you're going to do it. I suppose there's probably another way to do it, but this is the easiest, most logical way. And let's go back here. We'll do that. Let's just go to Google and say, Google, tell me about the x86 CMP instruction. Just to read it from another source so that we know that we're not just making this all up. Comparison instructions. Performs a bitwise logical and I don't want to deal with that. Compare. Performs a comparison operation between arg1 and arg2. The comparison is performed by a signed subtraction of arg1 from arg2, the results of which can be called temp. Is this right? Really? if it will be extended the E flags in the same manner. Yeah, I don't know. That's not really doing us any favors. Let's see if we can find something else. Let's go here. We went to this article once before, somewhat recently, if I recall. Doesn't see. There we go. Data movement. Let's see if maybe we can dig out a compare. This article seems to sort of break it down in control flow instructions. Jump condition. Compare. Compares the values of two specified operands, setting the condition codes in the machine status word appropriately. This instruction is equivalent to the sub instruction, except the result of the subtraction is discarded instead of replacing the first operand. It's great. If the 4 bytes stored at var are equal to the 4 byte jump to location labeled loop. So basically, if you substitute machine status word for the flags register, it's actually the E flags register. Or at least that's my understanding, is that it's just called E flags in the technical sense. But basically, it's telling you the same thing. It's comparing the values of two operands, and then it's taking in some way, it is codifying the result of the comparison in a register that is then tested by conditional jumps. These instructions, what are conditional jumps according to this article? These instructions are conditional jumps that are based on the status of a set of conditions that are stored in a special register called the machine status word. All right, we're just going to use that so I don't have to substitute it all the time. But machine status word, E flags register, we're not going to differentiate. We're just going to say that those are synonymous for now. The contents of the machine status word include information about the last arithmetic operation performed. For example, one bit of this word indicates that the last result was 0. Another indicates that the last result was negative. Based on these condition codes, a number of conditional jumps can be performed. For example, the JZ, that is okay. So if you're not chuckling to yourself, then you should be. The JZ instruction, otherwise known as Rockefeller, the JZ instruction performs a jump to the specified operand label if the result of the last arithmetic operation was 0. Otherwise, control proceeds to the next instruction in sequence. A number of the conditional branches are given names that are intuitively based on the last operation performed, being a special compare instruction, CMP, which is down here. For example, conditional branches such as JLE and JNE are based on first performing a CMP operation on the desired operands. It's probably enough for now. We have enough to basically, we know now why CMPs are based or sort of followed by conditional jumps, because conditional jumps test the E flags register, or the flags register, if you will, that have been set, or that has been set by a previous or a prior compare instruction. It's possible that maybe we're just mixing this up, or not mixing it up, but I just want to say x86 E flags. Wikipedia, tell me about the flags register. The flags register is the status register in Intel x86 processors that contains the current state. This register is 16 bits wide. Its successors, E flags and R flags, are 32 and 64 bits wide, so there's some difference right there. The wider registers retain compatibility with their smaller processors. And you can see right here that, let's talk about the bits in the flags register. The first one, 0 bit, is the carry flag, and then the first bit is, or the second bit, as the case may be, is reserved. And you have parity flag and adjust flag and 0 flag, sign flag, all this kind of stuff. And E flags has more. The use. I don't really want to talk about pushing and popping quite yet. The flags register. Let's check status register. Let's ask Wikipedia. Tell me about the machine status. Nope, it doesn't know anything about that. Status register in a traditional includes at least 3 central flags, 0, carry, and overflow, which are set or cleared automatically as side effects of arithmetic operations. That's kind of what one of the previous things we were reading was. Basically, CMP is sort of just a subtraction, and then it will just test these flags to say, is it equal to, is it less than, equal to, or above than whatever it's being compared to. They may then be tested via conditional branch or jump instructions. A status register may often have other fields as well, such as more specialized flags, interrupt enable bits, and other things that we are not going to concern ourselves with. And if you really want to read about the zero flag and how this stuff is implemented in the carry flag, then you can just click on it. The carry flag is a single bit in the system status register used to indicate when an arithmetic carry or borrow has been generated by the ALU. So again, the rabbit hole goes very, 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 very deep when you're getting into this stuff. But on an abstract level, I mean, we haven't actually written a single line of code. So again, we're just sitting here talking, but I'm just talking here. The CMP, how it's implemented under the hood, you have to understand how the CMP works because there is a sort of ghost, or there's an invisible man behind the curtain for how the CMP is, how comparisons and tests and things like that are implemented in the context of architectures and computers and things like that. But for our purposes, it is good enough to simply say that there is a register behind the scenes. The flags register is what we will call it. I'm not going to make any different distinction between E flags and things like that. There's a flags register that in some way stores the result of a comparison such that we can use conditional jumps to branch execution based on whatever is stored in the flags register by a previous comparison operation. If you do it's worth noting that if you do a comparison and then you dick around with the flags register, the conditional jump will have no idea that you sort of have some code in between these two that is messing around with the register. So if you really wanted to, you could just change the result of the flags register, and then you could totally alter program flow just by doing that. Because JNE, might no longer, it might not be equal. So you have to be careful when you're doing this stuff, but more often than not, and we'll just scroll down here a little bit. It's a long video and whatnot, but here's a comparison, here's a conditional jump, here's a comparison, here's a conditional jump, here's a comparison, conditional jump, comparison, jump, comparison, jump, comparison, jump. It's pretty interesting. Every time we see a comparison, we're seeing a jump. That's not an accident, as we have talked about. Here's an unconditional jump. It doesn't matter if there's a comparison because as soon as it hits this, it's just going to say, oh, okay, well, now I'm going here. Here's a comparison, conditional jump, unconditional jump. We'll go a little bit deeper or a little bit farther as the case may be. All right, we'll go back up. And basically, you've obviously by now, or perhaps not obviously, but you should certainly be noticing these little lines that Cheat Engine is painting for you. And Cheat Engine obviously knows how this stuff works because it's making this nice, happy display for you. So here's a comparison and here's a conditional jump. And what Cheat Engine is saying, well, here's this line. And what it's saying is if the result of this comparison is such that this unconditional or that this conditional jump is executed, then just follow this line. I'm going to go, it gets lost in the sauce down here, but I want to say it's probably like right there. It might be here or here. I don't know. You can look. Just say, what is it? 223E, 223E. It's going here. So if you have 1,000 jumps going on, then these lines get real crazy, and you have to actually look at the address. And then, well, 223E, 223E is right here. So go there, do that. But again, you can see that Cheat Engine is sort of connecting the dots for you and making it easier for you to follow the execution path of a program, as it were. Here's a comparison. Here's a conditional jump. If this conditional jump is true, then it will go here and it will call this procedure, function, whatever. If it is not, then it will just fall through and go push and then call and then pop and then call and then compare. And then if this conditional jump is true, it will just go down here and then it'll do this and that. If this conditional jump is not true, it will push -1, then it'll call this, then it'll pop that, and then it'll do the exclusive OR, and then it's going to return. I don't know where it's returning to or whatever. I'm not making that distinction, but this is sort of when you're digging through assembly code in the memory viewer here, this is how you're going to basically say or figure out how because all this stuff is executed sequentially. You're going to be like, all right, well, it's doing this instruction, that, so on and so forth. It's going to call this, it'll return eventually, and then I'm going to call that, and it'll return eventually. Then I'm going to do this comparison, and then I'm going to check with this conditional jump what the result of that comparison was. I might go here, or I might not. I might go here. It all depends on what the result of the comparison is. And that is how basic control flow exists in assembly. So let's close this, let's close this, let's close that, and let's just stop and actually use some of this to our advantage in the next video.